Hello, everybody. Welcome to today's lecture. This is the first in a series of 3 lectures on organic chemistry. We're going to go over some of the basics today. So recall that organic chemistry is the chemistry of carbon atoms. Now, carbon atoms have a unique ability to combine easily with other carbon atoms and hydrogen atoms and halogens and oxygens and nitrogens. Remember, carbon has 4 locations where it can form covalent bonds, which leads to a multitude of different variations that can be used to form a variety of compounds. In fact, almost 98% of the compounds known to man are organic compounds. We're going to look today mainly at the compounds formed when carbon shares bonds with other carbon atoms and with hydrogen atoms. And if you want to kind of review nomenclature, there's an excellent website here where there's a link in my PowerPoint. You can click it and go to that link and practice after the lesson is over. We're first going to discuss how you can take a complex mixture of hydrocarbons, which are found in petroleum products that are extracted from the earth. Petroleum, of course, comes from the decay of old plant and animal material that are, in some cases, millions of years old. The anaerobic decomposition, meaning the decomposition without air present, leads to the formation of a variety of organic compounds stored under the ground, and we can tap into that. So the principal fractions that are separated from this crude oil mixture are shown below here. The number of carbon atoms in the chains are shown. So you can see from when they have 1 to 4 carbon atoms, typically those molecules have weak forces of attraction. So they're gases at 0 degrees Celsius. And of course, as you get longer carbon changes, forces of attraction get stronger, and the melting points change accordingly. So we can take a mixture and heat them up in a fractionating tower and separate the various components. So here's an example of a separation of 4 different components using differences in boiling points. They're all heated in the absence of air, and the vapors rise in the fractioning tower. And of course, as they rise, they cool, and the different fractions will condense from that liquid at different temperatures. So to show you here a little simulation, we're going to have here are 4 fractions here that we're going to separate. So they go in the fractioning tower and get heated, and as they rise, some fractions like gasoline are removed near the top of the fractioning tower, and asphalt comes out at the bottom of the fractioning tower. And as you go up the tower, of course, there's decreasing melting points for each of these substances. And we use the difference in the melting point to separate the various fractions in crude oil. So there's a picture of one, and there are many, many different organic compounds, as I mentioned, and carbon can also share electrons with oxygen, nitrogen, and sulfur atoms. Those are called heteroatoms to refer to the fact that they're not carbon or hydrogen, and they influence the properties greatly. For instance, if you ever smelled skunk scent has sulfur in it. It's a 2-carbon molecule, where very similar to ethanol, except the oxygen is replaced by sulfur. And that gives it that unique property, that very strong scent that we all learn to avoid from an early age. Other scentful organic compounds are called esters. An ester, in this case, methyl octanoate, is a organic compound again. To refresh your memories, or if you haven't taken it before, the oct means 8. So there's 8 carbons in a chain here on the left side of this double bond O. And on the right side, there's a single carbon. And this particular ester comes from an alcohol reacting with an acid. So we have an organic acid on the left, we have an alcohol on the right. They combine, water is removed, you end up, the name comes from the alcohol it came from, in this case methanol, and the acid was octanoic acid. When those two combine, you get an ester, very, very distinctive odor from esters. Esters are fairly easy to make in an organic chemistry lab. I know that I used to do ester formations in high school labs with students, and some of them have pleasant smells. A lot of the artificial flavorings used in the food industry are in fact edible esters. So here's a chart showing a bunch of different classes of hydrocarbons. So we start with alkanes. The significance of the ANE tells us it's a straight chain carbon hydrogen containing molecule. In this case, it's got 6 carbons, so we call it hexane. And here's a typical example. This one would be called ethane or ethane. All aliphatics, which are straight chain carbon atoms, end in ANE, the name. So the significance of ENE tells us that someplace in the carbon chain there's a double bond. And the naming convention we use is we change the name to distinguish it from the alkanes by using ENE at the end of the name. So you can see in this example, 1-pentene, the ENE tells us there's a double bond. The number 1 tells us it's between the first carbon and the second carbon. In fact, when we number aliphatic chains, we number them according to where the double bond is. And we follow the same convention for a triple bond between carbon atoms and change the name to YNE. So we call these alkynes. And this particular example is called 2-octane. Again, the oct means 8 carbons in the chain. The 2 means the triple bond occurs between the second and the third carbon. Now, we can have other types of atoms bonded to carbon besides hydrogen. We can have oxygen. And if you have an OH functional group bonded to a carbon chain, we call those, collectively, we call them alcohols. So, and in this case, 1-butanol refers to the fact on the first carbon, we have an OH group. So we always number the carbon chain when there's a functional group or a double bond, so you use the lowest possible numbers. We're going to go over that naming convention in the second lecture in more detail. So now we can add halogens, which are group 17 atoms. They are very reactive because they have 7 valence shell electrons and they want to become more stable by acquiring an 8th. So they react very easily with alkenes and break the double bond and make what we call alkyl halides. So in this case, 1-bromohexane, it's a 6-carbon chain, and bromine is attached to the first carbon. That's where the 1-bromo comes from. Now we can get 2 alcohols combining together and releasing a water molecule, in which case we end up with what we call an ether. An ether has an oxygen in the middle of a chain. In this case, one of the alcohols would have been methanol, and the other alcohol would have been 1-propanol. So if we have 1-propanol and methanol combining through a dehydration, we get an ether. We'll talk about that again in more detail later on in one of the following lectures. So the naming convention we use to name ethers is the longer of the 2 carbon chains is the parent chain. In this case, it's 3 carbons, so we call it a propane. And the shorter chain is named as a side chain. Since there's oxygen in the chain, we use the prefix oxy here in its name. So 1-methoxy means on the first carbon, there is an oxygen with 1 carbon attached to it. So you could conceivably take this OCH3 and put it on the second carbon, in which case you would have 2-methoxy propane. So the name below it is an old style name. In this particular course, we're only going to require you to remember the conventional names derived from the rules that are suggested by the International Union of Pure and Applied Chemists, IUPAC or IUPAC for short. And nitrogen is a very important substance present in the living world. It's found in amino acids, which are the building blocks of all proteins. Most of our dry mass is made up of protein. And the convention for amines, when they have nitrogen attached to 2 hydrogen attached to a carbon chain, we use the naming convention again. This is a 3-carbon chain, so it's a propane. And the side chain, in this case, attached to the first carbon, is called amino. So this particular example is called 1-amino propane, where we have a side chain and a parent chain in the name. To show you a few more, if we take an alcohol and oxidize it, then we can create an aldehyde. If the alcohol is an OH group at the end of the carbon chain, they develop aldehydes. If the alcohol is on a carbon other than the end carbon, we end up with compounds called ketones. So the naming conventions, again, to go over it here, those are both called carbonyl groups, but if a carbonyl group is attached to an N carbon, like I said, you produce an aldehyde. If the carbonyl group is attached to a carbon that's not at the end of the carbon chain, then it's called a ketone. And the name ends in either Al or One. So in this case, butanal means it's a 4-carbon chain. The end carbon is always carbon number 1. And that's where the end of the name comes from, Al, and the 4 carbons give it the butan. For the second example here, we have a carbon chain of 6 carbons, and on the 3rd carbon from the end of the chain is the carbonyl group. So the name ends in One. We call this 3-hexanone. Note that it's never called 4-hexanone because we could use a lower numbering system starting from the left carbon and moving to the right. And that's just the convention that's used by organic chemists when naming compounds. Now, if we continue oxidizing, we can end up with a carboxylic acid. If you oxidize an aldehyde, you can get a carboxylic acid, which is a carbonyl group really attached to an alcohol. But it's neither a carbonyl group or an alcohol. We now classify it as a carboxylic acid because its properties are different than either an aldehyde or an alcohol. And the naming convention here is a 4-carbon acid is going to start with but. So we call this butanoic acid. The OIC in the name tells us it's an acid. The butan tells us it's a 4-carbon chain. And the first carbon is always the acid carbon. Now, if we take an acid and combine it with an alcohol, we end up with an ester, as I've mentioned before. So you can spot the part of the molecule that comes from the acid by looking at where the double bond O is. The carbon that's double bonded to the oxygen is always considered to be the acid part of the molecule. It was derived in this case from butanoic acid, and the oxygen side with the single bond is considered the alcohol portion of the molecule. So this would be called methyl for methyl alcohol, methyl butanoate. And the end of the name changes to OATE if it's an ester. So a few more examples here. If we take ammonia and react with a carboxylic acid, you end up with an amide. So one of the primary chemicals used to discourage mosquitoes is in fact an amide. DEET is the short name for that. And again, here you can see the naming convention is 4 carbons mean it's going to start with butan. And since it's a C double bond O NH2, the name changes to amide at the end. The name below is the common name, and the name on top, butanamide, is the systematic name. Okay, now carbons are singled out because they form 4 strong covalent bonds with one another, and they can form these long chains. Now, when we show them in straight lines, that's a bit of an exaggeration. The bonding arrangements are not really straight, they're really bent, but it's convenient when you're drawing them on paper to simply show them as straight lines, just to make it easier to fit them into various spaces. You can see here are 2 different components of gasoline. The first one here on the left, you can see it's got a 5-carbon chain, so we call it pentane, and there's 1 carbon side chains attached to the 2nd carbon here. We call that a methyl group. There's a methyl group attached to the 2nd carbon in the chain, so we call this a 2,2,4, because there's methyl groups on the 2nd carbon and the 4th carbon. This is carbon number 1 over here. Typically, gasoline is rated according to how the gasoline mixture burns compared to a pure 2,2,4-trimethyl pentane concoction that burns. So N-heptane is something that, in fact, when it burns explosively. It doesn't burn smoothly, so it can cause engine knocking. So it's much preferred to have branched hydrocarbon chains in your gasoline mixture to avoid engine knocking. Now, they also put additives in like tetraethyl lead, but that's been banned because of the damage done by the lead over time. It's bioaccumulated and, of course, had some severe side effects on people. So now the N simply means it's a normal straight chain with no branching. Hept tells us it's 7 carbons. So realistically, even though it's drawn like this for convenience, more appropriately, it would look like this. So because the carbon atoms, of course, are bonded not by straight lines, but they go in angles here of about 109 degrees. So again, I've mentioned about octane ratings. The octane rating compares the gasoline mixture to the burning properties of a 2,2,4-trimethylpentane. So I expect on any evaluation, you can just draw straight line diagrams like this. You can use compressed or condensed structural formulas if you want, or you could show all the hydrogens with sticks if you want, and I'll show you that later. So now, other mixtures of gasoline don't burn very well. Like I said, N-methyl, N-heptane, by the way, doesn't burn very well. So if we said that the octane rating of a gasoline mixture was 87, that means it would burn comparably to a mixture of 87% 2,2,4-trimethylpentane and 13% N-heptane. So as the octane rating increases, the amount of straight chain hydrocarbons is reduced in favor of increased numbers of branch chains. So again, here is what a heptane typically is drawn like, but this curved structure here is probably a better representation of what it actually looks like because of the way that carbon bonds with not only carbon atoms, but the hydrogen atoms in a tetrahedral arrangement. So here's an example. Here's a curiosity of a compound that's got 122 consecutive carbon-carbon bonds. It's a very potent toxin. It's a natural poison. It's found in seaweed-like coral in Hawaii, and if you happen to ingest it, you usually die. So just showing you this for interest. You can see all the different functional groups. You can see there's lots of OH groups, alcohol groups here, and there's oxygens in the middle of chains, so kind of ether linkages there. There's an amine as well. So very complex molecule, very toxic. So some natives use poisons extracted from nature to immobilize animals when they're hunting them. One such poison is called curare that they extract from plants, and they use blowguns to shoot them at animals, and it paralyzes the animal so they can capture it and eat it. So now, where we're going to be going is we're going to be covering all these different transformations in our 3 lectures, showing all the different functional groups and how they can be transformed from one functional group to another through simple chemical reactions. A lot of cases involving water, in some cases just involving oxidations with various oxidizing reagents. So we start really with a triple bonded substance like alkyne, and we can add hydrogen to it to break one of those triple bonds and make an alkene. And then, of course, we can add more hydrogen to it and turn it into an alkane, or we could add a alkyl halide and make a chlorinated structure or a brominated structure. In this case, I'm showing you a chlorinated structure, and we call those halogenated hydrocarbons. And then we can take an alkene and react it with water and make an alcohol out of it. And we can dehydrate the alcohols and make ethers out of them by taking water out of that alcohol. Using 2 alcohol molecules and removing a water produces an ether. We can oxidize our alcohol by using oxidizing agents that we talked about in the previous unit. And we can, depending on where the OH group is on the alcohol, we can either make a ketone or we can make an aldehyde. The alcohol is on an N carbon, we make an aldehyde. If it's on a middle carbon, we make it into a ketone by oxidizing it. Then we can take our aldehyde and oxidize it further and make an organic acid, which is a C double bond OOH. The R simply tells us that is variable. And we can then take the organic acid, combine it with an alcohol, the OH group here, and make an ester. We can also take our organic acid and add NH2 groups to it using ammonia or other amino-containing compounds and make amides. So that's what we're going to be covering essentially in the next couple of lectures, all these transformations. Now, you will be allowed to use a sheet for your final exam that basically summarizes all these. Now, you should be able to recognize those functional groups by the arrangements of atoms, like I said, and you can then identify the family that they belong to, and you should be able to name the compound, which I'll go over in more detail in the next lecture. So now, typically the simplest organic compounds are simply called hydrocarbons. Like the simplest one is methane, a single carbon bonded to 4 hydrogen atoms. And it's a tetrahedral structure, as we mentioned. It's a 440 is a number code we can use to identify the type of bonding that's gone on and the shape of the molecule. There's 4 pairs of electrons surrounding the central atom bonded to 4 atoms with no unshared pairs. That's what those 3 numbers mean, if you recall from a previous chemistry course. So here's an example of various diagrams we can use to try and represent these molecules. You can see the bonds between the carbon and the hydrogen atoms are all 109 degrees and a little bit. So in the second diagram here, we can see that some of the bonds actually come out of the paper and some are behind the paper, assuming that we're looking at this in 2 dimensions. So the carbon and these 2 hydrogens would all be in the same plane, the same straight line, the same flat piece of paper, but one of the hydrogen atoms would be behind and the other hydrogen atom would be in front of that straight piece of paper. So that's basically what that means. And we can use a ball and stick model. I'm going to show you a program called Chem Sketch that will enable you to draw your own diagrams of molecules and then create these stick structures, or to create these space filling model structures, whichever you prefer. All of them can be used to symbolize the 3-dimensional structure of molecules. So again, as I've mentioned, if there's an ordinary plane, straight plane, pretend the screen is a flat piece of paper, one hydrogen atom would be coming out from the paper and the other hydrogen atom would be going behind the paper, and that's what this type of structure represents. Now we have a 2-carbon alkane in this case. It's all straight single bonds. That's why we group it into the family called alkanes. And if we are going to show it again using structures with different bonds, these 2 hydrogen atoms would be coming out of the paper. These hydrogen atoms would be going backwards behind the paper, and the rest, these 2 carbon atoms and these 2 hydrogens, are in the same plane, right on the plane of the screen, computer screen. And a space filling model for this ethane would look like this. Now you can write condensed structural formulas. Instead of drawing it like this all the time, you could simply show it as this carbon's bonded to 3 hydrogens, this carbon's bonded to 2 hydrogens, and this carbon's bonded to 3 hydrogens. So another way of representing this molecule of propane. So here are some other examples. This would be ethine, only one hydrogen. Now, one thing I always check when I'm drawing to make sure I've done it correctly is that every carbon has 4 bonds associated with it. So you can see from the example of ethine, this carbon has 3 bonds between this carbon and the carbon adjacent, and the carbon also has 1 bond with the hydrogen. So there's 4 bonds surrounding this carbon. There's also 4 bonds surrounding this carbon. So similarly, when you check this carbon, it's got 4 bonds around it. This carbon has, it's bonded to the adjacent carbon here, 1 bond, and it's bonded to 2 hydrogen atoms. That's a total of 3, and then it's bonded to that carbon for a total of 4. And the naming convention we use, it's got 4 carbons in the chain, so we use but for short form meaning 4. It's got a triple bond, so it ends in YNE, and it happens between the first and second carbon. That's where the number 1 came from. And the third example on this page, you can see again, it's got 1, 2, 3, 4, 5 carbon atoms. And when we number the chain, we typically number the chain so we encounter the double or the triple bond with the lowest possible number. It takes precedence over the side chain. So in this case, the side chain is attached to the second carbon from the left, but when we number the chain, we're going to number it from the right because we encounter the triple bond with the lowest number. Going right to left, we would encounter it with the second carbon. Going left to right, we encounter it with the third carbon. So we're going to number it from right to left. So we're going to name this 4-methyl because on the 4th carbon, as we number right to left, 1, carbon 2, carbon 3, carbon 4, there is a 1 carbon side chain on the 4th carbon. So that's 4-methyl is the side chain. And the triple bond in this case is on the 2nd carbon. So we call it 2. And since it's 5 carbons, we go pentyne to represent the triple bond, and the triple bonds on the 2nd carbon. Now I'll be going over that in more detail in future. So now we can also use just straight line structures. If you don't want to show carbon and hydrogen atoms, it's implied that each location here is a carbon atom. So that would be 1, 2, 3, 4, 5 carbon atoms. There's no double or triple bond, so we would call that pentane, N-pentane, or just pentane. And in reality, the carbon atoms form a kind of a bent structure. This one below would be showing the hydrogens. So you can see that this N carbon has to have 3 hydrogens. That carbon has to have 2 hydrogens, 2 hydrogens, 2 hydrogens, and 3 hydrogens. So either way, you could show the same molecule of pentane. Now this is an isomer of pentane. Isomers are chemical compounds with the same formula, but different arrangements of their atoms. And in this case, we're going to call this a methyl butane because it's 4 carbons and there's a side chain here. Overall, the same number of carbon atoms, same number of hydrogen atoms. And a third way of showing it would look like this. A single carbon atom in the middle that's bonded to 4 CH3 groups. So these are all isomers of the same formula, but they all have different chemical properties. So they all have different names to represent those different compounds with different properties. So each of these lines represents, of course, chemical bonds. And wherever the lines meet or end, there's a carbon atom. And you also have to remember every carbon has to be accounted for 4 bonds. So that's why if there's 1 bond here, we need 3 hydrogens. This carbon has 2 bonds, so you're going to need 2 more hydrogens to complete the 4. So now let's talk a little bit about these structural isomers. As I said, they're the same formulas, but different structures, and there's different types of isomers that we can talk about. In this case, the parent chain is 5 carbons. In this case, it's 4 carbons with a side chain, and they both have the formula C5H12. So the left structure we're going to simply call pentane or N-pentane, meaning normal pentane. And the second one is a branched hydrocarbon, which we call methyl butane. Again, the butane comes from 4 carbons, and a single carbon side chain is called a methyl side chain. So there's no need to number it because if you think about it, if we only have a 4 carbon chain, we don't have to say 2-methyl butane because realistically, if the side chain's on the end, it's simply pentane. But if the side chain is on either this carbon or this carbon, it is simply going to be methylbutane. 2-methylbutane, 3-methylbutane are both not needed, of course. They don't follow the naming convention. There's only one place you can put a methyl group, and that's on the carbon that's second from the end of the chain. So 2 and 3-methyl butane would be the same structure, simply rotated and flipped around in space. So now a subgroup of structural isomers are called positional isomers. So with positional isomers, what you end up is, if you have an aliphatic chain here of carbon atoms, in this case we have 5 carbon atoms, there's a carbon atom at the end, 1, 2, 3, 4, 5, and there's a bromine attached to it. So we have a 1-bromopentane. So 1, 2, 3, 4, 5 carbons and a bromine attached to it. So in this case here, we still have a pentane and we have a bromine attached to the second carbon. So these are isomers of one another because the bromine is on a different carbon, either on the end carbon or on the second carbon. So I can show a compressed structural diagram showing all the hydrogen atoms, showing this again, CH3, CH2, CH2, CH, CH3, with the bromine on the second carbon from the end rather than the end carbon. And the third one shows the bromine. There's 3 possible locations where I can put bromine on a pentane chain. So we have to distinguish where the bromine is, and that is what we do in positional isomers, indicating the location of, in this case, the bromine atom. They all have the same formula, C5H11Br. So that's what makes them isomers of one another, in this case, positional isomers. So geometric isomers occur when you have the same formula and same atoms, but they're arranged in space slightly differently, almost like a left hand and a right hand for a glove. So in this case, when you have double bonds between carbon atoms, you cannot rotate the carbon atoms in these double bonds. But you can rotate in the single bond. So I could take this carbon atom and rotate it 360 degrees as I could over here, which happens in real time with molecules, of course. But with the double bond, there is a limited rotation. And that's because the double bond, if you remember, the carbon-carbon bond here, one of the bonds is from an sp2 hybrid between these 2 carbon atoms. But the second bond, is actually a pi bond that's formed from an unused p orbital from each carbon atom. There's an unused p orbital in this carbon atom and an unused p orbital in this carbon atom, and they form a second bond that's called a pi bond. And that pi bond really exists above the plane and below the plane of the carbon atoms, whereas the other double bond, part of the double bond, is called a sigma bond. And that the electrons tend to be localized between the carbon atoms in the sigma bond. So one of the double bonds is a sigma bond, the other double bond is a pi bond. And it's the pi bond that's weaker than the sigma bond because the electrons are further away from the carbon atoms. They're more susceptible to attack. So you can use halogens or water or other substances to break one of the double bonds and create another compound. So frequently happens in the synthesis of different organic compounds. Now, what you have to note here is, again, the terminology we use. Cis means the 2 groups on either side of the double bond are on the same side, or they can be on opposite sides. And we talk a lot about this in fats. We talk about cis fats and trans fats. It turns out the fatty acids that make up the triglycerides found in the human body are primarily of the cis variety. They're almost all of the cis variety. The trans variety fats that we sometimes make when we chemically alter vegetable oils into solid fats are simply not recognized by the body's enzymes, so they can't be broken down and they tend to bioaccumulate. And that's why some countries have actually outlawed the use of trans fats in their foods, which is not a bad idea because research shows that the trans fats accumulate and can cause problems in your circulatory system over time. So So each of these different types of geometric isomers has different chemical and physical properties because of the spacing of the functional groups are different. And in some cases, enzymes will recognize this arrangement, but they will not recognize the trans arrangement. So this particular alkane, note that the formula for alkanes is always CnH2n plus 2. So if it's C5, we would have H12. If it's C6, we would have H14. But with alkenes, you end up with CnH2n because we're taking 2 hydrogens off to make the double bond. So in an alkene, if you had C4, you would end up with H8. Now, the homework I'd like you to try after the lesson is on these pages, and here are some problems that you can start to practice. As well, I would encourage you to try to download a program called ChemSketch. ChemSketch is a very useful program that is a free download. If you just do a search for ACD ChemSketch on the internet, you'll be able to find it and download it, and it's tremendously useful. You can draw your own organic structures, and there's a tool that enables you to click it and it tells you the name of it. So it can help you not only learn the functional groups, but learn how to name them as well. And I can speak from firsthand that I really enjoy using this program. I'm gonna just boot it up here for a second. And I have created a video that shows a little bit more. I'm just gonna show a little bit today. So if you select the right tools, you can just basically then start clicking atoms, and if I want to put another group on here, I could put, for instance, an amino group on here and on here. And then if I wanted to get the name, I can click draw and then click the box here and then click this little tool that says generate a name, and there it is. 3-methylpentane, 1,2-diamine is the way that this program has decided to name this compound. So again, you can see the URL here at the bottom, but if you just do a search on ACD ChemSketch, you'll be able to find this. So I encourage you to download ChemSketch and start playing with it to learn how to name and draw structures of organic compounds. There's lots to learn, of course, and we have a very limited amount of time to do so. So we're just going to scratch the surface of organic chemistry, just enough to get you started. So nothing too onerous, I hope. Well, that's the end of today's lesson. Please practice your homework and work hard. Remember, there's no substitute for hard work. So again, thank you very much for tuning in today.